Hi, and welcome to another exciting edition of, this is Mathematics series here, and we're doing linear algebra, and the vectors are getting to more of your Calculus 3. But this is for hyperactive students, and my name is Nate Nessler. Now, I know math's a little scary, but we'll keep it real simple. We won't use any crazy technical terms for mathematics as much as possible in order to simplify things some more. And we'll keep things a little more basic, if you will. Now this is something that you'll see in Calculus 3. Sometimes you'll see it in some of your other mathematics too, but it's not bad. This is one of the easier parts of Calculus 3. There's definitely hard parts of Calculus 3, but this is not really one of the harder parts. So thankfully this is a simpler thing. And this is also used a lot in physics, and we use it like crazy in 3D graphics. So you absolutely have to know this. Now what we're going to cover is vectors. And basically this is a directional pointer, or a line, if you will, that has a length to it, and the length is what's called, has a name for it called magnitude. And the magnitude of a vector you can think of as like the force. So the force at which you would hit something at, within a certain direction, that would be the magnitude of that vector. So we can use that in order to do calculations for physics. We can also use it for doing other things, for drawing the graphics, for shading and stuff like that. Oftentimes when we're doing our shading and our graphics, we don't want the force, we want just the direction of the vector, and the direction is the only thing that matters to us. And we use this all the time for doing 3D graphics and games. Games live and are built off of this. I mean, it's in almost every calculation you can think of practically in a game. So it's vectors and matrices the whole time, pretty much. There's very little that you do that doesn't involve vectors and matrices in computer graphics. So it's very important that you learn this and get this down very good in a very adequate manner, so that you can do the calculations and understand the mathematics behind the programming, so you can understand and manipulate and create new graphics techniques for future game development and things of this nature. And not just that, but implement other people's papers and things of this nature for white papers. So with this, let's have a look at what we have here. Now, I just have a vector called A, and it's got a little arrow over it in order to let everyone know that, hey, this is a vector, and that's standard drawing methods for it. There's many ways to draw a vector, though. Some type will be like bolded A here, and that means a vector. You'll see lots of different ways of describing it. There's even like a little hat that you can draw over them, too, depending on, what... if you have a Componentwise setup or something like that, you'd have a little hat over it. But that's used a lot by physicists, and we'll get into that a little bit. But for right now, let's just have a look at what we're doing here. So it plots just like you're used to plotting points back in, basic algebra and, trigonometry. It's simple. So we're just going to go here along X. We're going to go 6 units over. PAL right there, and then we're going to go up 8 and plot that point. Now we're working from 0, 0, 0, center coordinate system here, world coordinate center, if you will, and we're just plotting that point. Now we can have a three-dimensional one here and have a third number here, and that'd be the z-axis, or shall I say the z-axis here in space. So that'd be your depth moving in and out of the screen, if you will. Okay, so that plots my point here at 6, 8. And if I draw from 0, 0 to 6, 8, I get this line, and that's the direction of my vector, right? And I draw an arrow here. Bam, there we go. You notice that this forms into a, 90-degree right-angled triangle. And that's awesome. We put a theta right here, and then we can sit there and use basically methods for doing triangle calculations for solving problems with our vectors. This lets us find out the length of this vector by using a triangle formula. And you've seen it before. A squared plus b squared equals c squared. I think everyone should be familiar with this from geometry that you took back in the day. This is standard high school material. If we have a squared here plus b squared and take the square root of both sides, that eliminates our squares on both ends. So that gets us down to just c, right? And then a squared plus b squared, if we add those together and take the square root of that, we can solve for c. So in this case, we have 6 here for a, right? So 6 squared plus 8 squared, because b is 8, right? and it becomes 36 plus 64. My apologies for my writing. I'm doing it with a mouse. The graphics tablet's back in the other office. And these added together, it becomes 100. And take the square root of 100, and you get 10. Very cool. And that becomes the magnitude of our vector, or shall we say, the length of our vector. And again, that's the magnitude is the length of the vector. Same thing. I can prove this. I've downloaded Sage, which is kind of like a more complicated version of Mathematica or MATLAB or Maple. And you can download it from Sage's website here at sagemath.org. And you will need to download also VMware. So vmware.com/products/player is where you're going to have to download that from. And you'll need that installed in order to access Sage and use it, because it's running in Ubuntu as a basically this is what VMware Player does. It lets you run another operating system within your operating system. So currently I'm running Ubuntu inside of Windows XP right now. So I can run multiple operating systems at the same time. That is possible to do, and you do that with VMware Player. So if you're interested in that, that's cool, blah, blah, blah. There it is. That's how you do it. And you just download this and install this. One of the things I have, another benefit, like I said before, I prefer NVIDIA cards. And my reasoning for that is if I come in here and I go into my virtual machine settings or whatever, and come down display, I can check this accelerate 3D graphics before I start up my virtual machine. And that allows me to accelerate the drawing and all the aspects of this player for the window interactions and such of the Ubuntu, because it's going to be running through the 3D graphics driver instead of just a regular standard visualization driver. So I get a massive speed up in my program. If I don't have NVIDIA installed, I'm not going to get that speed up. You know, if I have an ATI card or an Intel integrated, I'm not going to get it. You know, it makes use of the NVIDIA drivers, because NVIDIA is the only one that writes drivers that work real well on Linux for the most part. So, you know, that's certainly a benefit to it. And there's an example of why you want that. But if I just come in here real quick, and I create our vector, right? So A equals, and this is Python for the code for doing this thing. So you need to check out the Python series if this is confusing to you. Alright, so that's going to create a vector for A, right? I'll create a vector for B too while I'm at it. I don't know. Let's do... Oh, well, I kind of pre-calculated some stuff beforehand. I think it's 9 and 12 here. I'll double check. I wrote a short program in Python to auto-calculate a whole bunch of, and that's just the program there. And I just auto-calculated with 100 different variation numbers here the result of perfect squares, and then when they're added together, taking the square root of it in order to get a perfect result for the magnitude. So that way I don't have any decimal values, no remainders, more or less. You can do that with a modulus calculation, which basically checks, gives you the remainder, and if your remainder is 0, bam, there you are. Or I just checked for rounding it, you know, dropping off the value, and then if it didn't have, if it was equivalent to the original number after rounding, then it was, you know, a perfect number with no decimal. So after those two numbers were added together, they were a perfect square for taking the square root. Which is great, and this is what I'm getting here. So as you can see, we have a 9 and 12 gives me a result of 15 for my magnitude. And it was just faster it took me like 5 minutes to code it up, so it was fast and easy to do, and that just made the most sense. Alright, so I have my A vector here, blah blah blah. If I do A dot norm here, open close parentheses, this is going to calculate the magnitude. Bam, there it is, it's 10. So yes, verified that yes, we did our mathematical calculations correctly, and we did get 10. If I want to, I can sit here and do this part by part basis. So say I want to access the first element of A, which would be the 6 there for that vector, right? And I were to multiply it times 2. Not times 2, sorry, but take it to the, make it squared. This to take it to the power of 2. That's what the double multiply does. That's part of Python. They do also allow a caret top, which is not part of Python. So if you do want to do that method, meaning that I could sit here and say A 0 like this, and then I can do it to the caret. Where's the caret? Gotta find the caret first. There it is. Alright. And that works too, only in Sage though. If you want to use Python, you have to use the double multiply symbol like I was just using. Okay, cool. And then again, A here, 1, which would be the second element there, which is 8. Star twice here, 2, and then that'd be 64. If I add 36 plus 64, I get what? 100. That's right. Pow, there it is, 100. And of course, square root of 100 is, you got it, 10. And there we go. Awesome. So obviously this is great for many reasons. Now if I want to create a unit vector, as it's called, so say I only want the direction and I don't want, or normalize, it's referred to as normalizing a vector. You'll hear that most often in computer graphics. It goes by the same name as a unit vector, which means a vector that has a magnitude of 1 only. I can prove that, no problem. So I need to create my normalized vector. Well, it's quite simple really. If I just sit here and go, well, if I do A, now we already know that it's 10, right? And divide it by 10, right? And there you go. That'd be 3/5 and 4/5. Now I can prove that over here. Let's see here. Let's remove magnitude. And yeah, and if I'm doing the unit vector here, as you can see, I would divide my vector by the magnitude, and this gives me a unit vector. And I can prove that that actually works out, because if I go ahead and assign this to a whole nother vector here, where I do A divided by 10, right? Cool, that puts that result into C. And now let's do the magnitude of C. So if I do C dot norm, which we've already established that that works for doing the magnitude, and it's 1. So therefore we just created a unit vector that only gives us the direction and none of the actual force, because you know anything times 1 is itself, so that eliminates the force value. So that's awesome, and we'll use that like crazy for our mathematics on a regular basis, particularly light. If you don't do this on a surface, you'll end up with something like super bright or super dark, because you'll end up multiplying your color values and things of that nature and intensifying it in ways you don't really want to do. And that gets eliminated if you do it as a normalized vector, because then you only have the direction of the light or something like that across the surface, and not the magnitude of the vector in addition to the direction, which would mess up all your other values in your calculations. So quite often, in order to keep your calculations from getting screwed up for a lot of these mathematical operations that we're going to be doing in the 3D graphics, we have to normalize our vectors, or as you call it, a unit vector. We need unit vectors for our vectors. Well, let's just say normalize our vectors. That's easier. That's why we say that quite often in the film game industry. Okay, cool. Now let me go ahead and minimize that. And I just showed how that works for creating a unit vector, or normalized vector. Let's talk about something else. Now, because of the fact that we have, basically a triangle here, we can do all kinds of triangle calculations. So a lot of you may be familiar with SOHCAHTOA from high school or whatever. There's another way to remember this, and some old hippie caught another hippie tripping on acid. It's a little more colorful, but it's another way to remember it. I think some old hippie caught another hippie tripping on acid. It's a little easier way to remember it, but nonetheless, this works, and it works quite nicely. So basically this solves us for doing sine, cosine, or tangent here. And then arc sine, arc cos, and an arc tangent lets you get to the other side and solve for whatever it is you're looking for. And in this case I'm solving here for theta, by doing 8 over 10, because B and C, right? So what is it now? Opposite over hypotenuse, right? So opposite here is going to be from this point here, which is our world center point, would be B, right? That's the opposite from that side. Great. And of course A is going to be adjacent to it, so it's right next to it. And hypotenuse is the overhead part here. Okay, cool. So in this case we're going to have opposite B, which is 8, and then hypotenuse, which is C10 below it. Right. If we take the inverse sine, or arc sine of that, then we get our theta, which is going to be our angle there for our direction, and we can use this for all kinds of great calculations in order to find if it's in the view frustum of the camera, basically see if we're inside the camera or not. For our model, for geometry. For instance, we wouldn't want to draw geometry that's not in the camera. What's the point? If it's not going to be seen by anybody, there's no point in drawing it. So we can use this as a test to determine whether or not something needs to be drawn by the angle. So very cool. And this has a lot of applications and a lot of uses. So the opposite of a sine is an arc sine or inverse sine. Now there's multiple ways to write this, and I gave out several examples here. You can have it as sine with just a dash over here, which means like inverse sine or arc sine, as it's called. And I did an example here with a cos. I could have a sine here instead, which is arc sine. Another way is tan with a -1 here for a tangent here, inverse 1. I did a sine inverse 1 here too. That's the 3 different ways you can write it. So you can either write with just a dash here, an a in front of it, or a little -1 here. So no matter what, it all means inverse sine or inverse cosine or inverse tangent, whichever one it is. In this case, we're doing sine, so it's going to be inverse sine. And then 8/10 for calculating that value. Okay. And that's how you would solve that. Now, the cool thing here in Sage is that yes, you can do sines and all this other stuff. I didn't check to see for the hot sheets. Now they have some hot sheets on here, which are great for letting you know what the different functions are that you can use and can do with different things, which is great. But I'm not real sure if this particular one. They do have sine and they do have cosine and tangent and things of that nature. So, if you want to do all kinds of other type of calculations, you have them. For instance, pi is represented as pi. You have an e here for your, well, if you get into that kind of mathematics, you see what that is. I'm not going to get into it. Alright, so and then theta is literally spelled out as theta, so that's how you're going to represent theta. You can see sine is here, just like you expect it to be. Lambda, if you're familiar with that. And you can tell it to solve equations and all this fun stuff too. You can also test stuff to the limit, which is great if you're doing stuff for Calculus 1 and trying to understand derivatives and things of that nature. Also, you have derivatives here, and they need to do a diff in front of it in order to calculate a derivative. They also have integrals. So you can do an integral from Calculus 1, 2, and 3. Integral gets heavy into 2 and 3. You don't see integrals so much in 1. It's at the very end of 1 for the most part. It's like the very last thing you do. Integral is the opposite of a derivative. And a derivative is just a tangent to a curve. That'll be explained in the derivative series. Okay, so here's just some quick references, and it's great. You can download these straight from the website if you're interested in this kind of stuff here. If you're not, well, understood, but nonetheless, this is extremely useful, to say the least. And it's got a whole number of things in here that is really useful. Sometimes it's a little tricky to hunt down the particular thing you're looking for. Here's for how to do eSum. We'll get into eSums later. We'll need it for some of our formulas and our calculations. And here's what I'm talking about the limit. Yeah. So very cool. You can also plot graphs and things of that nature. It's not real straightforward or real simple, I'm afraid. So you probably won't want to do that too much or too often. I'd have to say that for a fact. It's really not simple. I couldn't believe how complicated it was compared to some of the other mathematics programs. But yeah, there's a lot of different methods you have here for doing different types of setups. And you can do all kinds of great and crazy things with this program. So it can be extremely useful for you. There's also a really nice calculator out there. It's called a TI CAS. And what it will allow you to do is not just graph a formula, but you can actually take the graph and then start manipulating and move it around. And literally it'll start updating and changing the algorithms on the fly. Extremely useful for doing 3D graphics, for creating formulas and figuring them out. So that makes it really nice, and it's a really slick calculator, so you might want to go check that out. They're not super expensive and they're extremely useful. Having a great calculator like that, and I do recommend the CAS because it's going to be the one that can do the calculus, and calculus 3 and all that stuff. The calculators that you had handheld are limited in their capability for doing calculus 3. It goes into any kind of real heavy graphing or something like that nature. You're pretty much going to have to use a computer, and you're going to have to use some kind of software like this one here. Or you're going to have to use something like MATLAB or Maple or Mathematica. It's about the only thing that can handle some of the upper calculations that are involved. This is Python, so you can import additional stuff for Python, which is great. And you get all kinds of wonderful capabilities with that. So if you're familiar with Python from the Python series, then you just got basically an easy way of expanding it, and you don't have to learn a whole new language just to do your mathematical operations, which is really nice. So, and you can also use this with your programs too, if you need to do any kind of higher calculations like this. It is possible to use this with programs. So Sage is nice. I'm not sure if I can do ArcSine. So I haven't checked this out. I haven't seen it. Venturing into dangerous waters here. Usually stuff is not recommended. Oh, buddy. Alright, so if I go in here, I say, it was B over C, right? So, yeah. Okay, interesting. It didn't quite give me what I wanted. Let's see here. 4/5, fine. Okay, so it's not giving me the value. There's something I'd have to do apparently to make it display the value. Not sure what that is on here. I've just started playing with the software just within the last 30 minutes, so before doing this video. But basically, if you ran this in a calculator, you can get this exact angle value here. Okay, so let's have a look at our other mathematical operations. Okay, so there's more that we can do than just this. We can also represent our vectors as I, J, and K. So this is what you see a component-wise method here for doing it in the way you would do for physics. Thankfully, we don't have to do what physicists do a lot of times here, but we do interact a lot with physics for our type of mathematics and for our 3D graphics programming and such. So you'll quite commonly see mathematical formulas done in a physics manner. So you'll run into this all too often. But for doing our actual programming, we don't really have to worry about this. So that's really great. So we get the most simplified version of everybody out there. I mean, other forms get quite complicated for the way they have to depict these vectors, and thankfully on the 3D animation side we get to depict it in the easiest way possible, and it works out the best for us because that's what's going to compute the fastest and the way we can code it the simplest. So of course the simpler you can code something, the faster it runs typically. So it's great, and that's what we want to do. So here we have I, J, and K. So think of it as like X, Y, and Z, or Z. I say Z for Z because it sounds like C and Z. They sound a lot like. So, Z as in Zachary. So I refer to it as Z here in the video. So if you're hearing me say Z, that's what I'm talking about. Okay. So they just basically, if you want to, translate this into a 3D graphics, think of this as I as X, J as Y, and then K as Z. And this really helps out. And this makes sense because 0 is for X here, 0 for Y, and then 0 and then 1 for Z. So full value of the Z axis here, and no values here for X and Y. Same thing goes for the J here. So no value at all for X here, no value for Z, and just Y is full value of 1 here. The same thing times 1 is itself. I here is 1 for X, and then 0 for Y, and then 0 for Z. So when you work this out, then it just makes a whole lot of sense. So let's pretend like A is 4, 5, and 3, and we've just expanded this out for our and this would be a hat and not a arrow when you go into this component-wise form here. And then so we have our 4i plus 5j plus 3k here. And let me go ahead and hide this graph because it's kind of getting a little bit messy. There he is. Really nice and clean and easy to see now. And this works out. See, because you can go from this component-wise method back to your regular method here. So 4, 5, 3, we can get back to that from this 4i plus 5j plus 3k. The way we do that is quite simple. We break it down to our component-wise method. So we go in here 4, so 4i here times our I method here. So we get 4 times 1 is 4, 4 times 0 is 0, 4 times 0 is 0, right? So we get 4, 0, 0. And then plus, see, just like this here, plus. And then 5 times the j here. So 5 times 0 is 0. 5 times 1 is 5. And 5 times 0 is 0. Okay? And that gives us our y, more or less. And then for our last one, our k here. So 3 times 0 is 0. 3 times 0 is 0. And 3 times 1 is 3. And of course this equals, well, what you expect. And these, I'm putting commas here so you can see the mathematical add operation. You can also do it as a vertical add in order to make it visually line up easier for rows and columns, more or less here. But if I add 4 to 0 here and that to 0 yet again, I get 4, right? Because 4 plus 0 is 4. And then 0 plus 5 plus 0 is 5. And 0 plus 0 plus 3 is 3. So here we go. We get back to the same thing as this here. So they're now identical. Awesome. So that's how you can go from this component-wise method back to your standard, method here. And it's just a different way of representing it that may work out better for certain calculations or whatnot. Okay, but again, we don't have to mess with that hardly ever for our particular setup, but we do see it in physics. Alright, so let's say I have b here is 3, 2, and just to show off some capabilities for a way you can do this stuff. Alright, say I want to add these together, right? Alright, no problem. And I can do the same thing here. I can say a plus b. Great. Remember, because a is what? 6 and 8. B is what? 9 and 12. So 6 plus 9 is 15, and 8 plus 12 is 20. If you want, I could even mix it up and create another one. Let's say d for our vector, right? Equals vector. And we'll make it just like these here, right? So I'll do b as, well, let's do d as the other a here. So it's what, 4 and 5, I think? Yeah. Okay, so 4 here, comma 5. Because I'm working off the old one here. Alright. Sorry, let me switch out that so it's not confusing. Because that is confusing. There we are. 4 and 5. It would so help if I didn't do... Hold on one second. Getting click happy. Alright. So I'm going between operating systems here, but I'm clicking back and forth with inside a VMware player here. Very cool. So there's our A here. So let's do our E equals vector, open parentheses, open bracket, 3 comma 2, close bracket, close parenthesis, entered. D plus E equals what? 7, 7. Just like what I have written right here. Right? And the reason why this works, well, just like I said, we do 4 plus 3 because these are both on your x-axis here, right? So 4 plus 3, we're adding the x's together and we're adding the y's together, and then we're going to add the z's together. In this case, it's just x and y, so it's 2D. But I could have 3D if I just had a whole nother number here at the end, and that would be my z-axis, and they would add together the exact same way. You just add the two z's together. So 5 plus 2 is what? 7. So there we are. We end up with 7, 7. Okay, and that's how you add two vectors. You can also do a scalar on one. So say we have our A here, and I multiply it times 2. Great. So it was normally 6 and 8 for our A. I'll show that again. But when I multiply it times 2, it works just the way you would think it would. You're going to have 2 times 6 is 12, and then 2 times 8 is going to be 16. Perfect. And then that's how a scalar is going to work, as it's called. And scalar is just a fancy name to say a number times a vector. That's it. And it's just an additional number here. So here's our scalar multiplication here. Alright, so hey, here's what you can see it right here. Alright, so I'm just doing 2 here, by 4, 5, it's going to give me 8 and 10, and I can prove that again real easily, because if I do 2 times d here, bam, there it is, 8 and 10, right? Because 2 times 4 is 8, and 2 times 5 is 10. Perfect. The way this works on a graph here is, right, so if we graph this out, we have 4 over and then up 5, and then if we multiply that times 2, you would get what? What would you expect to get? Double the length of that vector, right? It's exactly what happens. So this is a really cool way. That's why it's called scalar, because you can literally just scale the length of your vector up and down, the magnitude of your vector up and down. So if you want to suddenly make a character start running faster, simply just multiply it times some number for the vector of his directional, and he's running that many times faster. He's moving a lot quicker now for the force on him. That's it. That's all there is to it. Makes it simple, makes it real easy, makes it nice. So now you can just easily tie that to some game controller button or something like that. Based on how far they're pushing up that stick or whatever, you can use that to be a scalar multiplier, and then that will drive the force of the character, make them run faster, move faster across the scene. That simple. So here's a good example of how that mathematics works, and you can use it within a game. So scalars are extremely useful. Let's look at subtracting them. Now subtracting works exactly the same way that adding them did. So if I sit here and go d minus e here, right? Oh, it needs to be a couple of d. Case sensitive, meaning that uppercase and lowercase matter. Bam, there I get 1, 3, exactly just like I have here, right? Why is that? Because 4 minus 3 gives me 1, and 5 minus 2 gives me 3. Or we can draw it out in a vertical method here, where you can just makes it easier to line things up while you're doing your subtraction or adding. So here you can more visually easily see that 4 minus 3 is 1 for your x's, and this lines up all your y's right here. So 5 minus 2 is 3, and they just did this to make it visually pretty, so it's easier to follow for doing your subtractions and such in your additions. But that's how you add together the different components inside of a vector, and this is how you scale up a vector with a multiply. Now, don't get me wrong, you could also divide a vector here too. So if I did a divided by 2, now we did that earlier. Bam, there it is. Because it was 6 and 8, now it's 3 and 4, right? Cool. And we did the same thing when we were finding the magnitude. After we got the magnitude of the vector in order to create a normalized vector, right? Because I did a divided by its magnitude, which was 10, gives me 3, 5, and 4, 5 for the unit vector for our vector A. The unit vector of vector A is 3, 5, 4, 5. That's another way, the fancy way to say it in mathematics. But also you can refer to it as just normalizing vector A. And that's how we typically refer to it in 3D graphics. So you'll hear me say that quite often in the other videos. If you're you may need to come back to this video several times while we're doing the programming, so that way it makes sense as to what on earth we're actually doing. You may want to work out just a few things mathematically on paper, as what's going on underneath the hood of the programming, so that makes sense as to what we're actually doing on a physical level here with the actual code, so that way you understand what's happening with the code. It's really important that you understand what on earth the code is doing, not just go, oh, okay, I know what that command does or whatever there. It's really important that you have a good understanding of how it works underneath the hood, because if you do, then you're open to do whatever you want to do and not just reproduce what someone else has already done. So that's the important aspect of this, and that's why it's so important that you learn this mathematics. Alright, so that's the basic part here for the vectors. Now we're going to get into some fancier stuff here in the vectors here in just a bit, and we'll look at dot product and cross product next, and those are some things from Calculus 3, but it's really simple. Again, very simple with these vectors, and it'll make life a lot easier for doing certain things like view frustum calling, and it'll also make it nice and easy for us to find the normals on our surface by doing a cross product, which makes it's how we find the 90-degree angle vector coming from two vectors that are intersecting, or shall I say x vector, y vector, and then a z vector here. You know what I mean? So basically we can find our normal direction coming off of our face. I'll get into that in just a bit and show you how that happens. But if you looked at the other videos on like the model view matrix and things of that nature for object space and world space, I go into a good explanation of what's happening with those normals and such. So You may need to refer back over to those videos. If you haven't seen them, you may want to check them out and purchase them so that you have an understanding of what's going on here and why we're doing the mathematics that we're doing. But I'll pull up that in the 3D program and show you a little bit of what we're doing and why it matters a bit. All right, so with that, it's great. Let's look at the next video. And again, my name is Nate Nestler. This has been for Hyperactive Studios for linear algebra with, well, this is calculus algebra for vectors. Sometimes it gets coupled with the linear algebra. Thank you very much.